Okay, this is going to be a quick couple examples for some half-life problems. The half-life of uranium-238 is 4,500 million years, so uranium-238 doesn't decay all that quickly. A sample of soil is tested and is approximately 0.0001% uranium-238. How much would have existed a billion years ago? Okay, so what we have in this what happened there? What we have in this example is a current amount and at T of 0.0001%. Is that right? 1, 2, 3 zeros. Yep. We have a time, which is 1 billion years. We have a half-life, which is 4.5 times 10 to the 6 years, or to 10 to the 9 years. It says 4,500 million years, so 4,500 times 10 to the 6 years, but I just moved it over 3 more times to make it 4.5 times 10 to the 9 years. And so it wants to know what the original amount was. So in a half-life decay, the amount left is equal to the original amount times 1/2 to the power time over half-life. So with that in hand, I'm going to say that my current amount, 0.0001%. My original amount, 1/2 of my time, which is 1 times 10 to the 9, divided by my half-life, which is 4.5 times 10 to the 9. The times 10 to the 9s here cancel out, and I just have 1 over 1.45. 1 over 4.5, I mean, which means 0.0001%. My original amount, half to the 0.22. Can do that on my calculator. 0.5 to the 0.22. So 0.0001% is equal to NO 0.86. And now dividing both sides by 0.86. I get an original amount of 0.000116%. So not much change there, but with such an incredibly long half-life, it's not that surprising. But originally I would have had 0.000116% uranium-238, and that's been reduced to 0.0001% over that number of years. The radioactive sample will be dangerous until the radiation is reduced to 6.25% of its original level. If the half-life of the sample is 34 minutes, how long will it take? So these questions require a little bit of math that we haven't done yet, called logarithms. So when we do these problems, we're going to have to assume that the amount that we've been reduced to is some integer number of half-lives and just figure that out. So let's say, for example, that we want to get to 6.25% of our original amount. Hold on. So we want our current amount to be 6.25% of our original amount. To make the math easy here, I'm just going to say my original amount was 100%. And so I'm using this formula. To predict a future amount given a half-life. So I have 6.25% remaining of my 100%, and that's going to be 1/2 t to my half-life. Now, dividing both sides by 100%, or really not doing anything, just dividing by 1, I get 0.0625, or you can just say I just converted my percentage to a decimal. Half-life t over half-life there. So what I have to figure out is what exponent do I put on half to get 0.625. Now using my calculator, I'm just going to keep guessing until I get it right. So if I put 1/2 to the 1, obviously that's just going to be 0.5. What if I put 1/2 to the 2? Well, that works out to be 0.25. 1/2 to the 3, which is 0.125, or 1/2 to the 4, which gets us 0.0625. I can do this on my calculator easily by going 0.5 times 0.5 and just keep hitting equals until I get to, or just keep multiplying by 0.5 until I get to the desired answer. But what I can see is 1/2 to the 4 is equal to 0.0625, and that is equal to 1/2 t over half-life. So t over half-life is equal to 4. This works because I chose 6.25% carefully as a factor of 1/2. If it wasn't, you would just keep going until you went past it, and then you'd have to estimate to some extent or learn about logarithms. Anyway, so my time is equal to 4 of my half-lives. Each half-life is 34 minutes long. And so this is going to take 136 minutes. So this sample will be reduced to 6.25% of its original life, which we said will make it safe, after 136 minutes. So if we wanted to do any work with that sample, we just have to avoid it for that period of time.